use a slightly different version, full swing one. Say, here there is no replica circuit to control the current at the operating point and the GM. Here, see, we can adjust that current by adjusting this supply voltage. Maybe we can use some LDO voltage regulator to adjust the VDD. Okay, we can adjust the VDD anyway. Then we can use a full VDD swing differential amplifier here. Say, the same circuit here. See, we have around 100K resistor to pick up this common mode output voltage, right? So this should be my common mode output voltage. We can replace these two resistors by switched capacitor CMFB circuit. Okay, it requires some clocking. Yeah, for this simulation, we need the ideal op-amp for maybe voltage gain of 30 or 100 or something like that. But in your home, you have to replace this one by some transistor, active load one. Okay. Yeah, like that. So you may use some current source, or maybe you can use something like that. Okay. Anyway, you can use something like that. You can use some small current. The purpose of homework 10 is minimum power. Okay. You can reduce this power to set voltage gain of 100. Okay. Then you can reduce VDD as much as possible. Say, then you need a small current here too. Yeah, for that case, we have two gain stages here. We need a definitely frequency compensation there. A simple capacitor, or maybe you may need something like a RC series feedback for frequency compensation. Okay. Yeah, other than this VDD, this is the same as the preceding circuit. Question? This is OO, right? This is VB. Actually, this VB thing is just a logic threshold, right? Of this inverter. The same VDD. Yeah, this is VB. So this means my common mode output at the same voltage level as a logic threshold, right? So input common mode is the same as output common mode. Okay, any question? Nope. Okay, let's just simulate it. Let's look at the code. Yeah, I think this is same code except this VDD, right? This is, just 1 by 3. Oh, this is multiplied by 2, then it's 2 by 3, right? And then this is 3 by 1 multiplied by 2. This is 6 by 1 for PMOS, okay? Yeah, this is my inverter 2. Because I have two inverters. This inverter is just no multiplication, right? 1 by 3, 3 by 1. Inverter 10 is just 10 times of this. So 1 by 3, 3 by 1, it's multiplied by 10. And then, let's just see. Yeah, supply voltage is fixed this time. You have to adjust this one to reduce power, right? Okay. Actually, you are free to change W of L. Yeah, also VDD. You are free. Okay, so here let's just see. Yeah, I have IPOM just 10, inverter 10. I have inverter 10 here. IPOM. OM, okay, and then I have another inverter 10, this is inverter 10. OP. And then what is the XP thing? Oh, this is GPOM. Oh yeah, that's the one. This is the one, right? GPOM. This is a GP. And I have inverted two. This is the one. Okay. I have two resistors here, 100K, 100K, 00, 00. And then I have a idea. Oh, this voltage source is only gain is 30. GP 0. This is positive. This is negative. So logic ratio. This VLT thing is, where is my VLT? Oh yeah, here. This is a small inverter. This is a VLT. Okay. Yeah, that's it. This is the circuit. This is somehow inverter 2. Maybe inverter 1 may not be enough for the common mode control. Okay. So I think this is the same, right? What's this thing? VIP is there. VIP is I am sweeping. Where is my input? Oh yeah, here. So I am doing the same thing, right? This IP is VIP, and then this thing is connected to DD, and then VIP, right? Yeah, that's voltage controlled voltage source. DDIM output is IP0, right? IP0 with a gain of 1. Okay, question? No? Okay. I need a full swing one. Oh yeah, here. Is this AC coupling? Oh, not AC coupling, right? Is this AC coupling here? Oh yeah, it is AC coupling. It's a slightly different from the previous version. The only difference is this one. I made that one into sub-circuit. And then huge capacitors. See, I have two differential amplifiers, and one will be connected to this differential mode input. The other thing will be connected to this common mode input. Okay. Simulate. Okay. This OP1, OM1 will be differential mode output. OP2, OM2 is my common mode output, okay? Differential mode output, common mode output. Ooh, I have a large gain for the differential mode, this yellow and red. See, how large? Yeah, this is so my 5 millivolt amplitude generate peak to peak 465 millivolt, right? 465. Gain is maybe around 90, right? 93 or something like that. That's a differential mode voltage gain. Well, the common mode is almost 0. How come? That's so small. Yeah, this is for the common mode. See, I will put common mode thing. Okay. Oh, how come I don't have delta? Huh. So I will do it again. My delta is 0.5. So my common mode gain is actually 0.5. Yeah, just 1/20th, okay? 0.05. So I reduced my common mode gain. That's pretty good, right? My differential mode gain is actually not 93, maybe 46, 46.5. That's my differential mode gain. And then for this one, my common mode gain is only 0.05. My CMLR is pretty good, right? 1800. I mean around 2000. 1800, around 2000, my CMLR. So, the only concern left is say you need a real op-amp for this one, a real amplifier, not this ideal amplifier. This ideal amplifier output resistance is 0, so you don't worry about the frequency compensation, right? For the real op-amp, you definitely need a frequency compensation for this common mode loop. Yeah, question? No? No problem? Okay, let's go to the homework again. Oh yeah, actually this is the one, the revised version, right? This is the one we just simulated. So you design an inverter-based fully differential, may not be fully differential, pseudo differential. You can use only MOS transistor RC, not this ideal op-amp. So you need a real differential amplifier for this one with a frequency compensation for that stage. And then DC gain, you need a DC gain of 100. So you can minimize VDD, and then you can minimize power, just get DC gain. And then you need to present, how come this should be present, Bode plot, DC gain, and VW with the different values of VDD. Yeah, there is a load here. Okay, one pop load each. Question? No question? Okay.